Hi guys. Hello. I figured, seeing as though that I have uninstalled Wuthering Waves, I can't use the game to make content. So unironically, it's forcing me to make content by other means. And I thought, how about we get a bit silly and maybe a little bit autistic with some interesting content, okay? This is either going to be a hit or a total miss, okay? I think we can all agree that in Wuthering Waves, there is a lot of interesting scientific concepts that they introduce. A lot of their world building revolves around weird science. You have like that retroactive rain. Gravity plays like a huge part in like the functioning and of like woo-wah. You have like all these weird concepts, frequencies, resonance frequencies, all this stuff, all this like gibberish of words that it's like a sci-fi almost, right? Sometimes the word can like feel like a sci-fi. So I thought, me being the absolute genius that I am, we are going to take concepts or things that happen in woo-wah and try to answer dumb questions with science. What the fuck do I know about anything? And you'd be absolutely right. What the fuck do I know? Listen, I'm a bit of a nerd. I'm dressed up. I've got my shirt on. I've got my tie on. You know what I mean? I expect you all to take notes because Professor Cabinetz is now in session, okay? If you want some lore about me, I used to teach kids. I say kids. I used to teach like 16 to 18-year-olds. Back when I was at university, okay? I went to uni for biochem. Why don't we talk about Augusta? Considering she's part of 2.6, we'll talk about a character and what she's all about, because both Augusta and Yuno, they have very different ways of controlling and harnessing power. Yuno uses the moon, and Augusta uses like electromagnetic radiation from the sun, which is wild, and she literally has the power of a sun in her sword. I don't know if you've seen her sword. She literally has a mini fuck-off sun inside of her weapon. Have you all seen that? How about we try and calculate just how powerful is Augusta really? How powerful is she actually? I will actually try and work it out. How much energy she's actually able to produce, and how strong is that really in terms of like human sense? Because I think that's kind of interesting to find out, right? So we're gonna go ahead and do that today. Here we have this circle that I have painted. It is yellow. This is the sun. And every sun is a star. It undergoes nuclear fusion of hydrogen to produce energy. That's how they make energy. And what's really interesting is we call stars black body radiators. That's the important thing. We call stars a black body radiator. And what that means is that a black body is an object that absorbs all energy that hits it, that is incident, we say, upon it. It absorbs all energy, and in return, it is able to emit it in the form of like thermal radiation in terms of heat. And from a star being, not everything is a perfect black body radiator, obviously. It shifts and changes, and we can measure that shift and change based on like color and wavelengths and different things of light. So we have black body radiators, and stars are considered, you know, black body radiators, but you can measure the wavelengths of light that they emit. You can see their color, right? Some stars appear more reddish in nature, and some stars appear bluer in nature, or more white or purer. They have different colors to them. That is due to their different wavelengths, right? Different colors of light have different wavelengths attached to them. The larger the wavelength, the less energy it has, the redder something gets. The shorter the wavelength, the more energy it has, the more blue it looks. That's why stars look different colors. Wow, it's crazy, isn't it? And from those colors, we can determine what temperature a star may be, which is pretty interesting. We could determine what its temperature of star may be. For example, 5,000 Kelvin, the star's going to be more in like the green yellowish range. It's going to appear more white. You have something which is like 4,000 Kelvin, which is going to appear redder. Okay, so you can actually look at the colors of the stars and the suns and see how hot they are going to be. And from from the wavelength of the star, you could determine kind of roughly what temperature it's going to be, which is very important in working out its temperature. Do you know what's interesting? You might look at this graph and be like, huh, that's pretty interesting. If you are saying that with shortened wavelengths and more bluer stars, why does the graph go to 0? Why is that? Why does it peak? Why does it peak? Why doesn't it go like continuously up forever? Why isn't it that like a purple star, an ultraviolet star exists? Why isn't it like 20 million bajillion Kelvin? Like why does it peak here and then suddenly trail off like crazy? If you thought that, you're very smart. Congratulations. You are in fact extremely smart for noticing this inconsistency in this graph. It's not linear. Yeah, the intensity of radiation to the wavelength, it's not a linear graph. And actually, it's the whole reason why like physical mechanics of like physics kind of broke down at this point, because people understood this and realized, wait, this doesn't make sense. This doesn't fit the laws that we currently abide by. It literally doesn't make sense. Energy is not linear. They found out energy is not linear, and particularly when it comes to like light, it's not linear. And then you had a really smart guy called, I believe his name was Max Planck. Okay, you had a really smart guy who kind of figured out, based from this graph and based from this concept, that energy isn't linear, and in fact is more about quanta. Energy comes in like packets. Energy comes in packets of like different types, different amounts of energy that we call quanta, and thus quantum mechanics was born. And Einstein took it further later on, which he got a Nobel Prize for, I believe. He took it further later on, and then that's the whole reason why we say photons are both wavelengths and like physical things that have their own like energy. He's the one who took that concept and ran with it, and we ended up with like the beginnings of quantum mechanics. This is why stars are so cool, and studying about space is like really cool, because a lot of the stuff we know now has come from looking at what's in our sky and trying to understand it. So I think it's like actually kind of interesting and wild. So from we have these curves, this graphs, we have Mr. Max Planck, we have Einstein, all coming together to completely revolutionize the way that we look at physics and the cosmos, which is pretty interesting. Anyway, that's just some backstory into this graph. Einstein and backstory into this graph. But from these things, we could kind of calculate. We could use this to actually answer our question. How much energy can Augusta produce by using the sun in her weapon? There is actually a law that we can use. It's called the Stefan-Boltzmann's law. And the Stefan-Boltzmann's law tells us we can work out the luminosity of a star. Okay? We can actually work out the luminosity of a star. And luminosity is essentially power. That's what we want. It's another word for power. And we can then use that to figure out how much energy Augusta could actually use. And this is where I'm gonna need to like start writing with my hands. Lumine, yeah, we're gonna work out lumines. No, we're gonna work out power, okay, which is denoted by L. Okay, L for luminosity. Okay, L for luminosity. Oh, can I go down? Okay, L, right, which is the equivalent to 4 pi r squared. Alrighty, 4 pi r squared. 4 pi r squared is wild. So like I don't know how do I describe, like it's like this is like, as things get bigger, it's like things get like exponentially bigger, kind of like this is a really bad graph. We have theta, which is, okay, this is the constant. This is the constant, okay? This is the Stefan-Boltzmann's constant. All right, you don't need to work out how you get the Stefan-Boltzmann's constant. It involves like Planck and his derivatives and stuff like that. It's his whole thing. It's his whole thing. We don't need to worry about it. You just have to accept that it exists, okay? You have to accept that it exists, okay? Which is, by the way, something like It is like I think that's the Stefan-Boltzmann constant. 5.67 times 10 to the minus 8. The temperature to the power of 4. Okay. This is how we figure it out. 4 pi r squared times by the Stefan-Boltzmann constant times by temperature to the power of 4. So there is an important thing that we need to find out here. There are two things that we need. We need the radius, and we need the temperature. T is in Kelvin, right? Yes. Whenever in this sort of stuff, whenever you're talking about temperature, it's in kelvins. It's not Celsius or anything like that. We deal with kelvins, okay? Every time. We're always dealing with shit in Kelvin, right? So we have to decide what we want. Okay, let me find Augusta's sword, right? As you can see, there is a sun in the middle of her weapon. This is why we're asking this question, okay? Just how much energy is this sun able to emit? Chat, how big do we think this sun is? By the way, this could never happen in reality. If you could ever produce something so small that's able to undergo like hydrogen fusion in order to generate power, that would be so insane. It would literally make a black hole. Like this is, you could never have a sun this small in reality. Like you would literally just make a black hole because it would be so dense. The gravity, it will collapse under its own gravity. So like, this is obviously the most insane hypothetical ever, obviously. 4 inches, as big as my balls, about the size of the palm of her hand. So I'd say 4 inches max. Okay, so we'd say the radius is like 2 inches. So we're gonna translate this. So we have 4 pi 0.05 squared. That's how small, bro. If this ever existed, we would literally be generating like a black hole. We would literally be generating a black hole. This is so dumb. This is so dumb. Okay, so 4 pi r squared. I had a calculator. Give me a scientific calculator. 0.0025 times by 0.0025. Okay, 4 pi r squared, 0.0025 times by 12.56, which is 0.0314. Yippee! 0.0314. Okay, we've done the first part. We've done the first part. 0.0314. Great, awesome. Now what's next? We have to times it by the Stefan-Boltzmann's constant. Okay, the reason why is because you just do. You just do. Okay, you don't ask why. You just do. Now that we have this, let's go to the second part. 0.0314 times by 5.67 times 10 to the minus 8. 5.67 times 10 to the minus 8, which we go here. 1.78 times 10 to the minus 9, which is 1.78 times 10 to the minus 9. A lot of tables and graphs. I remember when I studied thermo, need to refer to the tables. That's just it for a lot of stuff, isn't it? Just look at the table and just figure it out. Just pick the information that you need. We have all of this so far. And now we need to multiply this by T4, which is the temperature to the power of 4. Okay. But now we come across our second problem. Our second problem is, what the fuck is T? What the fuck is T? What is the temperature? Guys, how the fuck do we work out what the temperature of Augusta's sword is? How do we do that? How the fuck do we do that? Tectone? How do we do that? And again, we could go back to what we were discussing earlier, where different colors of stars inherently have different temperatures, okay? The whiter the star, the higher the temperature is to a certain point, right? Like our sun looks kind of white. It's kind of in that, it's in the mid sort of like temperature range in terms of like stars overall. The redder stars tend to be way cooler. So we can kind of look at Augusta's and be like, I'm gonna be real, this is kind of like yellow orange to me. I don't know how you guys feel. Would you guys agree that like the sun here is maybe a bit warmer? And so for that reason, I'd say we could probably put the temperature maybe like the average between red and yellow. Yeah, I'd say like maybe we should like put it towards like the 4,500 Kelvin range, just for like argument's sake. For argument's sake, how hot is our sun? How hot is our sun? Okay, so our sun is like 5,700 Kelvin. So I'm gonna say like Augusta's weapon is way like redder in nature than like our sun. Let's just go with like 4,000 Kelvin. I think that's like a safe bet. I think that's a safe bet, honestly. So T we're gonna put down as being like 4,000 Kelvin. If the sword gets that hot, does she vaporize upon using it? Listen, we can discuss that. Let me duplicate this. So we have, how much did I say? 4,000 Kelvin. 4,000 Kelvin. Oh boy. To the power of 4. Big number. Huge number, in fact. Huge. This is a massive number that I'm not even gonna write out. I'm not even gonna write out. Huge. Okay, but we're multiplying it by a very, very small number. We're multiplying this by a very, very small number, don't forget. So we have that big, massive number by doing T4, but now we're multiplying it by a very, very, very small number. A very, very small number times 10 to the minus 9 to be exact. It's a very teeny tiny small number. Okay, times 10 to the minus 9. That's right? 1.7 times 10 to the minus 9 times T4. Is this a 455,680? 455,680. That's 455,680 watts, which is going to be 455 megawatts of power. Yeah, so we end up with 455 megawatts of power. If we assume 2 inches of a 4-inch in diameter sized sun. A 4-inch in diameter sized sun ends up with 455 megawatts of power, assuming it's 4,000 Kelvin. That's kind of wild, man. Density needs to be considered at that size, I think. Why? We're just assuming, the way that we've worked this out, we're just assuming that the sun in Augusta's weapon is just a very simple black body. We're just assuming the sun is just a black body radiator. Density doesn't matter. Density doesn't matter because you can kind of like assume temperature based on wavelength. There is like a correlation between it, so you can just kind of plug in the numbers. Like if we wanted to include like other things such as like the rate of like nuclear fusion inside of like the star, that's a whole different topic. And that will take us a lot longer to explain. This is kind of easy to explain. Assume the radius of the star is 2 inches. From the wavelength of light, we assume the temperature to be 4,000 Kelvin. Why are you suddenly using dumb units side to side with actual sides unit? So, listen, y'all are a bunch of Americans. The reason why is because you're all a bunch of Americans, okay? And fantasy units like inches, foots, and buttholes are not useful for... Yeah, it's not useful. Especially in this stuff, you have to get everything to their base units. It's important.
Twitch.tv/Captain Cabinetz, Captain Cabinetz.
He's black!